Hello, welcome back to Math 332. In this video, we are going to look at some of the very important concepts in linear algebra, namely row space, column space, and null space of a matrix. And the reason why they are important is because the solutions for this system of equations depends very much intricately linked, in fact, with the concept of column space and the null space of a matrix. So we're going to look at that. We're going to look at the theorems, which tells us when the system of equations has the solutions. There's the existence of solutions, and when they have a solutions, whether or not we have only one solutions or infinitely many solutions, that is the uniqueness of this solution. So we have the existence and uniqueness problems that we need to solve for the system AX equal to B, and we will look at all of that in this video. So let's start by looking at the definitions. So suppose you have a matrix A of size m by n. So this is the standard way of writing the entries of a matrix, obviously. So say, for example, A12, A12 here, the first one, the first indices here basically indicates the row for this entry. So this entry is in the first row and second column. So we know all that already. So if you have given a matrix of size m by n, so we have m rows, so there are m of the rows. So these are considered as a row vectors. These are considered as a row vectors of matrix A. So these are considered as a row vectors of matrix A. So this is how you write them. And so as you can see from the size of the matrix, the row vectors is actually an element in Rn. All right, so because they have n entries, so you can look at right here, the second number here indicates the entry, so n of them. So that's the row vectors. Now, so if you look at the columns, so these are the first column of the matrix, second column of the matrix, and the n column of this matrix. And you can see if you write this as column vectors, so we write them as like column vectors C1, C2, and all the way to Cn. These are referred to as the column vectors of this matrix. So these are the column vectors of the matrix A, column vectors of the matrix A, and these are the row vectors of the matrix A, row vectors of the matrix A. And we haven't talked about row space yet. We just talk about the row vectors and column vectors. So what are the row space? So the row space is once you have all the row vectors and you consider all the possible linear combinations of the row vectors, aka span, right? The span of all these vectors. So if you look at all the row vectors and look at the span of all these row vectors, it will form a vector space. We know that long time ago that span of any vectors, which is a set of all the linear combination of those vectors, form a vector space. So this is a vector space, and these are known as a row space of A. So because all the row vectors is the Rn vectors, so the row space of A, which is the span of all the row vectors, is actually a subspace of Rn. This is actually a subspace of Rn. Okay, so the same thing if you look at all the column vectors. So these are all the column vectors of the matrix A, and instead looking at the column vectors, we look at the span, the linear combination of the column vectors. So these are column vectors. So linear combination of these column vectors again is a vector space, and it's going to be denoted as CA. This is a column space of matrix A, and actually all these column vectors is an element in Rm. Okay, so the column vectors is actually a subspace of Rm. Okay, sorry, the column space is a subspace of Rm. Okay, which consists of not the column vectors, but the span of the column vectors. So that's how we define row space and column space. The null space is a little bit different. So the null space, again, you have matrix A. So the null space of a matrix A is defined, right? So here, the size of the matrix is m by n, right? So we are looking at the collection, the sets of all the vectors, which is coming from Rn, such that the Ax equals to 0. So again, right here, this is all the x that is in Rn, and so you are looking at all the x, vector x's on Rn, such that A of x will be a 0 vectors. So this is the m by 1 0 vectors, this is m by n, this is n by 1. That's the reason why here x is in Rn. So the null space are not looking at the rows or not looking at the column, but in fact we are looking at all the solutions for this homogeneous system. So recall, a system like that is known as a linear homogeneous system. So we are looking at all the solutions. So we are looking at all the solutions for this homogeneous system. And obviously, it is not empty. There's always a solution for Ax equal to 0. So what is that? So if you look at the set, the elements of the set, so let me go here. And so, right, so if you have matrix A, right, how do you make it 0? So this is m by n, right? So if you multiply a 0 vectors right here of size n by 1, so you get a 0 vectors of size n by 1. So this solutions, okay, if you're looking at solution that will make ax equal to 0, this is one of the solutions. So the null space of A always contain a vectors, a 0 vectors. This is a 0 vectors in Rn. So it might contain some of the vectors, but it will definitely contain this vectors. And in fact, this is no surprise, because this is not a big surprise, because null space of A is again a vector space. So a vector space, and actually it's a vector subspace of Rn. So it will contain the 0 in Rn, and that's the 0 in Rn. So null space is actually a vector space. Okay, you can prove that. Take two elements from this set and add them. You will see that they're still in the set, and scalar multiple is still in the set. So it's closed under addition and scalar multiplications. It's like a two-line proof to show that it is a vector space. So that's not difficult. So so that's the null space. So row space is a span of the row vectors. Column space is the span of the column vectors. Null space is not span of anything. It is actually the solutions for the homogeneous system. So these are the basic, okay, very important concept, very important subspaces of Rn and Rm, which corresponds to a particular matrix of size m by n. Okay, so what we want to study is the relationship, right, among the solution for this linear system and how is it connected to the row space, column space, and the null space of this coefficient matrix that we want to study. And actually, do we have any connection between row space, column space, null space, and all that? So this is what we're going to study later. But before we give our first very important theorem, this is a general reminder of how we multiply matrices. We talked about that before, a long time ago, actually, in fact, kind of like in the first week of class, when we try to learn how to multiply matrices. And I mentioned that, hey, if you multiply matrices, so you have like A and B, you do the row, column multiplication. Observe that if you have a matrix A of this form and X is this form, you multiply them out, it will look very special. So this is the kind of like review, okay, of what we have learned in the first week of class. So let me say that again carefully. So you have a matrix A. So again, notation wise, you have to be very careful, because sometimes we use a C as a number, but here actually C stands for the column vector. So you can see this like first column, this column vectors of A. And then this is like the second column, it's called C2, and all the way to Cn. And then X is column vectors, so it's a vectors. The entries is x1, x2, all the way to xn. So all this x1, x2, all the way to xn, these are real numbers. These are real numbers. These are all real numbers, okay? And if you multiply them, A of A multiply X, so what will happen? So if you multiply them, you will see that you will get x1. If you multiply ax, you will see that ax is x1, this number here, multiply this column vectors, okay? And then x2, which is a number, and then multiply this second column, all the way to xn, which is a number, multiply this n column. So if you multiply ax, you will get that. And this is an expression that we have seen. You should be able to recognize in like 0.1 nanosecond that expressions that looks like this will be in the span of all these column vectors. Why is that so? Because this is exactly a linear combination. So linear combinations of the column vectors. So span is a collection of all the possible linear combination of the column vectors. So obviously this is in this set. All right. So now this is just a review of what we have learned just by multiplying matrices. It's something easy. Now we're going to give you the first theorem. This theorem is very important. So this is theorem 4.7.1. So what it says is that if you have a linear system, ax equal to b, if this linear system is consistent, right? Consistent means has a solution. So a linear system, ax equal to b, is consistent if and only if b, this vector b, is in the column space of A. It's in the column space of A. So this, again, this is a theorem on both sides. So if and only if. So it says that if a system of linear equation ax equal to b has a solution, then that b must be in the column space of A, which means b must be written as a linear combination of the column vectors. In other directions is, okay, if you have a b which is in the column space of A, then the system ax equal to b will have solutions. All right, so that's what it said. The proof is very straightforward once you figure out how you multiply matrices. All right, so let's look at this part. So this part here means that if, right, if the system has a solutions. So if the system has a solutions, and let's assume the solution are x1 all the way to xn. So if the system has the solutions, we have this equation, and we multiply out the left-hand side. As I said, if you multiply the left-hand side, you get this. This is from the observation above. So if you multiply out the left-hand side with A, with the columns, and x as this one, so you get x of x1 of c1 and all that linear combination of the column vectors equal to b. That means that your b, which is this, which is written as a linear combination of the column vectors, which is in the span of it. So b is actually an element, is the span of the column vectors, which is known as the column space of A. So what it says is that if A, x equal to b has a solution, and the solution is this one, then your B can be written as a linear combination of the column vectors. Hence, by definitions, your B is in the span of the column vectors, which by definitions is called the column space of A. So we done it. If the system has a solution, B, then B is in the column space of A. Okay. Now, what happens on the other side? So now, if you want to prove the other side, you will have to assume this. So if B is in the column space of A, then you want to show that AX equal to B has a solutions. Now, if B is in the column space of A, means that B can be written as a linear combination of the column vectors, which means they automatically exist. All these numbers, these are numbers. All these numbers exist so that your B can be written as K1 of this, K2 of this, all the way to Kn of this. That is because B is in the column space of A. So it's spanned by the column vectors. Spanned by the column vectors means this. Okay, matrix multiplications come in. So this part here, this part right here, if you write it out, this part right here, if you write out in matrices, these are column vectors, these are column vectors. Again, this is coming from the observations we have from first week of class. So this part here is actually this matrix multiplication. So you will see that this is the A, and you have this matrix, this entries, K1 all the way to Kn equals to B. That means that AX equals to B has a solution. What is the solution? The solution is this. The solution is coming from how you combine the column vectors. So you remember we adjust the scalar so that what B can be written as a scalar multiplication of this and the sum of all this. So you adjust all the K1 and K2 such that B will be equal to this. And that adjustment right here is the solutions for AX equal to B. So we have proof that, okay, we have proof that whether or not the system has a solution, it is completely depending on whether the B is in the column space of A or not. So this is critical, so critical that I am going to write it down right here, So AX equals to B, okay, has a solution or not completely depends on where is this B. If the B is in the column space of A, yeah, we have a solution. If B is not in the column space of A, no, we don't have a solution. So whether or not we have a solutions to the system AX equal to B, a non-homogeneous system, this B doesn't have to be 0. So this is called a non-homogeneous system. It's completely determined by where is B. Where is B? So these are all very important. When in the exam questions and the homework, you'll see that they've been twisted in so many different ways to test you on whether or not you understand this concept. All right, so existence of a solution. Do we have a solution or not? Existence of a solution will be completely depending on this B. So existent, all right? So existence will be completely depending on the B. Where is B? Okay, we haven't talked about what happens if you have a solutions. Do we have infinitely many solutions or just one solution? We haven't talked about that part yet, okay? That part will come later. Okay, so existence of a solutions will come from whether or not B is in the column space of A. Okay, all right. So this is a numerical computations of a system AX equals to B. Okay, so AX equal to B. So let's look at the first example here. So this is just an example. Okay, it's not a proof of anything. So this is our matrix A, this is a vector X, this is our B. And if you multiply this thing out and try to solve for it, I mean, we can solve for the X, right? So put this in the augmented matrix, suppress all the X1, X2, X3, so you know how augmented matrix works. So row reduce this augmented matrix to REF, then we see that we have a solution. In fact, the solution for X1, X2, X3 is unique. Oh, God. What's going on? Someone is calling. Okay, good, sorry. Okay, so back to this. Sorry. So back to this matrix, is try to solve for this x1, x2, and x3, and you find that x1, x2, and x3 are unique. They are 2, -1, and 3. Okay, because the REF matrix looks like this. So we have 2 of this, okay, -1 of this, and 3 of this will make this. So we'll see that if the system has a solution, this vector is clearly in the span of these 3 column vectors. This is a numerical computation. It's not, as this example, not really a proof. We have seen the proof, but this is like something that this numerical computation. Some people are more comfortable seeing numbers like this, but actually I will find a number like this doesn't really prove anything. It's easier to see things like this. But again, that's the difference between, I don't know, people who are not majoring in math. Math majors, so people will like that. It's kind of like, this is neat. This is pretty nice. But this is a numerical example. For some of you who like numerical example, this is like one way to say it. Now, the opposite way is the second example. So now we're not solving anything. I'm just saying that you have 3 of this and 2 of this and 4 of this make this. That means that the 37, 10, and 19, this vectors is in the span of all these 3 vectors. Then we will be able to write this thing right here as this. And in fact, this is going to be 3, this is going to be 2, this is going to be 4. So meaning that if you can, this thing is in the span of these 3 vectors, then the system has a solution. Okay, this is the other directions. If this system has a solution, then this B is in the span. This is kind of like 2 numerical example to show this 2 side of this theorem 4.7.1. Okay, which right here says that the system has the solutions, then this is in the span of the column vectors. If the B is in the span of the column vectors, then the system has the solutions. In fact, the solutions are this coefficient. Okay, enough of this. Let's look at the next theorem. This is tricky. I mean, not really tricky, but let's look at the terminology. So if you have AX equal to B, all right? Again, n by n for the matrix, n by 1 for the column vectors, n by 1 for those column vectors. This is a non-homogeneous system because the B might not be a 0 vectors. So if you look for the answers, if you look for it, okay? We don't know how, but let's say you found a solution. You found a solution. Apparently, A times X naught is B. So you found a solution. Then this solution is known as the particular solution of AX equal to B. So let's say you found a solution, okay? Then that solution is called a particular solution of AX equal to B. This is terminology. We haven't talked about anything yet. This is terminology to get into the next theorem. Okay, let's more example then. Let's say for example, this is our matrix A. This is our matrix A. This is a B, right? AX equal to B. Now, if you compute, if you actually do that computations, you will see that A, don't ask me how to get this yet, but let's say that if you actually compute, you'll see that this equals to 1, 5, 2, -3. We found them, let's say. So this is known as the particular solutions for AX equal to B. That's our X naught. So we found X naught such that AX naught equals to B, right? That's the B. So we found it. Somehow we found it. That solutions is known as a particular solution. This X naught. This is the X naught. This is a particular solutions for the system AX equal to B. Okay, that's the terminology. That's the terminology. All right. Now, since we are looking at this matrix, might as well ask you to do a few more things. So, all right. So if you compute the following, take the matrix A. That's the matrix A. Right, and if you compute -2, A multiply -2, 1, 0, 0, 0, you will get 0, 0, 0, 0. Okay, so this is an element that is in the null space of A. This is in the element, one of the elements in the null space of A. Right, that's the definition. Right, so null space of A are those X that solve AX equal to 0, 0. Okay. Now, if you do this computation, 1, 0, 3, 1, 0, you will also get 0, 0, 0, 0. So again, this is an element, not the null space. Null space is a vector space. This is an element, one of the things that is in the set, element in the null space of A. In fact, we can show that this is the basis for the null space of A, but we don't want to go that far yet, okay? So just some terminology. And this kind of vectors are known as the solutions for the system AX equal to 0, AX equal to 0, which is a homogeneous system, okay? All right, okay, cool. So this is some terminology. Now, let's look at the theorem now. Let's look at the theorem. Okay, so the theorem 4.7.2 says that if you look at the system AX equal to B and you found one of the solutions, you found one, X naught, that's the particular solutions of AX equal to B. And suppose, okay, you get sick and tired of this and you say, okay, I'm going to solve for this. Okay, you completely ignore the B. The B here, you completely ignore them and you say, I don't solve for B, I solve for the 0, which means that you drop the B, and you look at the system AX equal to 0 and you try to solve for it. And let's say you found a basis. So these are actually looking for the null space of A. And let's say you found a lot of vectors that actually span the space and all and this and that. And null space of A is a basis. It's a vector space, so you have a basis. So suppose the basis has vectors v1 all the way to vk. Okay, so the basis of the null space of A consists of vector v1 all the way to vk. That's what the starting statement say. Okay, the starting statement says that AX equal to B has X naught as a particular solutions. And if you look at the null space, these are the bases. That's what it said. Okay, then it says that once you have this two, okay, any solutions, it say that any solution of this AX equal to B must be in this form. Okay, that's what it said. All right, let me say that again. AX equal to B. You found a solution to that. AX naught is equal to B. AX naught is equal to B. You found a solution for that. And then you don't look at the B, you look at AX equal to 0, the homogeneous systems. You try to find the solutions, which means you try to figure out the null space of matrix A by definitions. You try to figure out the null space of matrix A. And since the null space of the matrix A is a basis, so they have some vectors, you try to identify those vectors and you found k of them. These are really the basis. So suppose you have these two. Okay, so suppose you have these two. These are null space, basis from the null space. Then theorem says that AX equal to B, the solution for this must be in this form, where X naught is a particular solution. V1, V2, Vk, these are the basis vectors. They are vectors in the basis of a null space of A. And C1, C2 are all numbers. These are not column vectors though. So these are the vectors. These are the vectors. These are the vectors. These are the vectors. C1, C2, these are numbers. So all the solutions will be in this form. All the solution of AX equal to B will be on this form. Okay, that's what the theorem says. Seems pretty straightforward. Okay, in fact, it's pretty straightforward because the proof is also pretty straightforward. So the proof is this. We want to show that this is the solutions. All the solutions for AX equal to B will be in this form. Okay, we want to show that all the solutions for AX equal to B will be in this form. So you multiply A on both sides and see what happens. So A of X, that's left-hand side, and then A of this whole thing here. Right, so A of X is here and A of the whole thing here. Now, so this is still AX, and then we have this, we cross, we multiply, we distribute. So AX naught is the first term, and we know AX naught equal to B. Why? Because that's how we define X naught. Okay, so AX naught is B. And then you can take the constant C1 out, and you have AV1, AV2, all the way to AVK. Now, this will give you 0. These are the 0 vectors. Okay, why is that? Because your V, how do you get a V, by the way? Your your V, right? These are basis vectors, right? Your V, these are a basis vector from the null space of A, which means if you are in the null space of A, your AV must be 0 because you're in the null space of A. Null space of A are all the vectors that do this. Okay, right? That do this. Okay, so you can see why your AV1 has to be 0 vectors, your AV2 has to be 0 vectors. So it doesn't really matter what are your C, because your C, whatever number is you have, multiply a 0 vectors is always 0. So you have all these 0, so you have AX equal to B. So AX equal to B, A of this X equal to B. So all the solutions for the system AX equal to B is like that. It can be written as X naught plus this, which is known as a general solution for AX equal to 0. This is written here. These are called the general solution for the homogeneous system AX equal to 0. So using this terminology, we know that solutions for AX equal to B is the sum of the particular solutions and the general solutions of the homogeneous system. So it's written in two parts. the first part. So the first part is, so the solution for this is consists of the particular solutions of this equations and the general solution of this equation. That's what the theorem say, and you can see from the proof. Now, there are many implications behind this. We are going to look at them, but there are many implications behind this. But before we look at the implication, I just want to say a little bit for those who have taken this 252 differential equation. So you have kind of heard of this terminology before. So let's say you want to solve dy dx, d2y dx squared plus 2y dy dx plus y equals to, let's say, ex. First, you don't solve the ex, you solve it equal to 0, find the so-called homogeneous answers. So let's say you found them, let's call it f1, f2, and then you try to find a particular solution, which is called fp, and then you say the general solutions is the sum of c1 of this, c2 of this, and then plus the particular solutions. So you come across this kind of terminology before. And these are linear differential equations. There's no surprise it's intricately linked to a linear system. But I just want to comment a little bit for those students who have taken 252 differential equation before. And when you solve a high-order linear differential equation, doesn't with non-homogeneous, so this is ex or sin x. There's techniques for you to find the particular solutions. There's a method of undetermined coefficient, this and that. But before you do that, you always drop it, make it 0, and try to solve this part here with the auxiliary equations that looks like this, plus 1 equal to 0, so on and so forth. So the terminology kind of matches because they are the same system. Okay, so we let's go back. This is enough tangent. So let's go back to this, and let's study this one more time. So this part right here, this theorem right here tells you about the uniqueness of a solution. If the solution exists, this theorem tells you under what circumstances you will have a unique solution. So let me go back to here. And let's review one very important concept in linear algebra, which I hope you still remember. So for any linear system, ax equal to b, we know, long time ago actually, that there are 3 possibilities. Number 1, no solutions. That's easy. Number 2, unique solutions. Means 1 solution. That's also easy. And then another case is that infinitely many solutions. And that's it. You can never find a solutions for ax equal to b. That you cannot find 3 solutions for ax equal to b. You cannot find 5 solutions to ax equal to b. That's not possible. Either no solutions, 1 solutions, or infinitely many solutions. There's just no way you can find exactly 5 solutions, and that's it. No. Okay, so there are 3 cases. So when is a system has a solution? When does it has a solution? So it has a solution. Okay, So whether or not it has solutions. So this means that exists, okay, solutions, or maybe solutions exist, okay? So is it unique? Is it infinitely many solutions? So the existent part, okay, whether or not we have a solution, that is given, we already know, by B. So if B is in the column space of A, yeah, we have solutions. How many? I don't know, but we have solutions. It could be unique, it could be infinitely many. All right, column space of A would not be able to tell you whether it's unique or infinitely many, but column space of A will be able to tell you whether we have or we do not have solutions. So if B is in the column space of A, we have solutions. If B is not in the column space of A, sorry, no solutions. It will be that. Does that make sense? Okay. All right, so theorem 4.7.2 actually answered this part. If we have a solutions, that's the reason why they say is that we have a solution. So if we have already a solution, we already have a solution, then infinitely or unique solutions will depend on this part, which is the basis for the null space of A. You see it? Do you know why we have infinitely many solutions if we have this part? Where do we have infinitely many solutions? Well, because the C here can be any numbers. So if you have, so let's say you have V1, the entire S only have 1 non-zero vectors, V1, basis, non-zero vectors. So this part are all gone, okay? So this part are all gone. So let's say you only have C1, V1. This will already give you infinitely many solutions because your C here can be any numbers. It can be any numbers. Okay, so theorem 4.7.2 is trying to tell you when you have a solution, whether or not your solution will be unique or infinitely many will be this. It will depend on this, which means will depends on the null space of A. It will completely depends on the null space of A. So let's look at the null space of A carefully again. So as you know, okay, so as you know from before, actually in this video actually, so null space of A is defined as all the x that is in Rn such that Ax equal to 0. Now, sometimes the only solution is 0. You can't find any other solutions. The only solution is 0. Sometimes your null space can be as small as that. And you also know from subspaces, you know this is a vector space. The smallest possible vector space is a set contains 0. So if your null space of A is so small that it's only this, then you actually do not have a basis. If I ask you to find a basis, what's the basis? What is the basis for the null space of A? The basis for a null space of A does not exist. You cannot say that the basis is 0, 0, 0. You can't say that. Why? Because a 0 vectors can never be independent. These 0 vectors can never be independent. So there's no way it can be a basis, because being a basis, you must be able to span the space, which this does, but it also needs to be independent, but there's no independent here, right? So there is no basis here. So when that happens, we will say that the dimensions of the null space of A is 0. Okay, what's the dimensions? Remember, the dimension of a subspace, you have to find a basis and count number of vector in the basis, but the basis, this is not a basis. The basis is actually empty sets. There's no basis, nothing in it. So if you want to count how many vectors in that basis, there's no basis, so it's 0. This is no surprise, right? So if your null space of A is so small that it only contains 0 vectors, which means there's no basis, which means that there is no this part whatsoever, then you have a unique solution, because this is the part that generate infinitely many solutions. So if you don't have this part, you have a unique solution. So the null space, if it is so small that it only contains the 0 vectors, then you have a unique solution. So back to here. Unique solution happens when the null space of A is just the 0 vectors. Then you have unique solutions. If your null space of A has more than one vector that is non-zero, let's say 1, 2, 3, whatever. Okay, let's say you have non-zero vectors like that. If you have one entry that's non-zero, then you know, well, we have infinitely many solutions, provided the solution exists. If you already know B is in C of A and null space of A has more than one non-zero vectors, then the system Ax equal to B has infinitely many solutions. Okay, so the uniqueness part, okay, whether it's unique or not, comes from the null space. And you can see so many exam questions just to test you on that. So yeah, get ready. So null space will tell you whether or not solution exists. If exists, is unique or not. Okay, but it will not be able to tell you whether the system has a solution. The system has a solution. It has nothing to do with null space. It has something to do with the column space. And that is like 20 multiple choice question right there. Okay, anyway, this is university and we are not studying for exam. I'm just saying, okay. All right, so that's the main part of it. This is the main part of it, of these sections. And I'm going to stop right here because I don't want to, the next part is kind of not quite related to this. So I don't want to go into that until you are completely clear on this sections. So the next sections we'll be looking at how to actually compute the null space of A, the column space of A, and the row space of A. So it's purely computational, like how do you actually find the basis for all this vector space. But remember, in these sections, we are using this null space and the row space and the column space to answer questions on solutions, existence and uniqueness of a solutions of a system of equations in the form of Ax equal to B. All right, so that's it. Thank you very much.